sodium chloride, strong electrolyte, weak electrolyte, non-electrolyte? Strong electrolyte. You can see the water molecules breaking apart the lattice there. We have the ions. It consists completely of ions. Do you see any molecules of sodium chloride present in liquid water? No. Sometimes, it's deceptive because sometimes ion will stick here to a chloride, but it won't last long. It will be broken apart again. Shortly thereafter. Copper 2 chloride in water. Well, copper 2 chloride is a soluble salt. Chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. So chloride is soluble salt. Soluble salts are strong electrolytes. So if we take a look here, we have some solid. It's blue. It's not because of the chloride ions. The blue comes from the copper ions. Now, which one are the coppers? Which ones are the chlorides here? When you look at this lattice, are the grays the chloride and the blues the copper? No. Actually, the grays are the copper and the blues are the chloride. This color scheme has nothing to do with the color of the crystals here. But anyway, this is the lattice, ionic lattice. It's soluble salt. It breaks up into ions. You can see the ions over there. So this is best represented by for every copper 2 ion, now this is a few plots. For every copper 2 ion, we have 2 chlorides. We have to maintain that ratio because that's the ratio of the formula. Interestingly, take a look. The red ends of the water molecules surround the copper 2. In fact, the red is oxygen. So oxygen has a negative charge bias, negative charge density. The hydrogen surround the chlorides. That helps stabilize the ions. Well, I break this up into 2 steps. The first step, for any solid like this or any liquid or whatever, I first ask myself, is it soluble? Well, this is an ionic compound. For ionic compounds, we know that group 1 are soluble, so it's soluble. And so this forms K2SO4 aqueous. And then after I look at solubility, then I look at electrolyte properties. I know it dissolves, but I ask myself this: does it dissociate completely, partially, or not at all? What would you say? Well, first I ask, is it a strong acid? No. Is it a strong base? No. Is it a soluble salt? Yes. Therefore, it's going to dissociate completely. Your book is going to do this. It's going to go straight to this. It's going to do it in one step here, which is okay too. This is perfectly fine. So you take this, and when you dissolve it in water, it's going to just break up into the ions. And the ratio is 2 to 1. For every sulfate, we have to have 2 potassiums. For every K2SO4, we have to have 2 potassiums. So it's got to maintain this ratio. It could be 2 dozen, 1 dozen. It could be 2 moles, 1 mole. 2 million, 1 million. It's just got to be this ratio. So that's called the stoichiometric ratio. What ions do we expect here? Well, first, does it dissolve? You check the anion. It dissolves. Nitrates are all soluble. It's nitrate. Okay, yeah, so it dissolves. Does it dissociate completely, partially, or not at all? Completely, soluble salt. And so what does this dissociate into? Calcium, what's the charge on calcium? 2 plus and nitrate. nitrate. And we have to have 2 nitrates. So we don't put the 2 down here, we put the 2 in the front. And so it'll look like,
How do you tell if it's a salt?
How do you tell if it's salt? If it's an ionic compound and it's not hydrogen, it's a salt. All ionic compounds are salts except for acids. Acids, we don't call salts. Acids are borderline molecular ionic. So ionic compounds are all salts. So we have a 1 calcium 2 plus and 2 nitrate. Aqueous just means dissolved in water. Aqueous. I should be writing these things now. And so calcium nitrate is a solid in pure form, but it can form a nice homogeneous solution. Calcium nitrate. Okay. Acids. You know, acids are a substance that has a proton that can be removed by water, or it can be removed by bases. It doesn't have to be removed. They're represented like this: HX or HA, where I represented A as an anion. This X is the anion here. So HX. This is what we call monoprotic acid. H2X is diprotic. H3X is triprotic. So HX would be like HCl. H2X would be like H2SO4. H3X would be like H3PO4. X is any negatively charged ion. This is a generic equation. This is a hydrolysis equation here. HX plus water yields H3O plus. H3O plus is called the hydronium ion. Next slide. As well as it's going to be charged hydrated. It's not hydrated. It's actually bonded good when the acid ionizes. And so this is called a hydrolysis. But we can also have an acid ionization reaction. There's HCl just goes to H plus Cl minus. Get rid of the water. Or we could have a hydrolysis reaction, HCl plus water, which is liquid, gives hydronium chloride. X, it can be monatomic or it can be polyatomic. Here's a polyatomic X, where X is nitrate. Here X is chloride. So we have this one. This one's called, what is this one called? HNO3. Nitric acid. Oh, so our question is does it ionize or hydrolyze completely, partially, or not at all? Well, then we have to recognize HCl strong acid, weak acid. What is it? Strong acid, hydrolyzes completely. HNO3, strong acid, weak acid, strong acid, hydrolyzes completely. There's a lot of stuff on this slide. There's not really a lot of stuff. Sorry, let me continue here with this. I know you're right. I'll post these slides. H2SO4, strong acid, weak acid? Strong acid. I hydrolyze it completely, but this is tricky because H2SO4 is a diprotic acid. Since it's a diprotic acid, do both hydrogens come off at the same time? That is, do the water molecules attack at the same instant? 3, 2, 1, attack, and then pull off the 2 hydrogens together simultaneously? Or do you think it happens one at a time? Like a water molecule comes, attacks, pulls off a hydrogen, another water molecule comes, attack, pulls off the second hydrogen. What do you think? A synchronized attack or a random attack? Random. It's going to be random. And so what happens is a water molecule comes along and pulls off a hydrogen. Comes along, pulls off a hydrogen, we form 1 hydronium and, what's this called? Bisulfate, or another word for bisulfate is hydrogen sulfate. Okay, now hydrogen sulfate is ready to be attacked again by another water molecule, except this time we ask ourselves, well, H2SO4, strong acid, weak acid? Well, it's a complete hydrolysis. But now this is not H2SO4, this is what? HSO4 minus. Is HSO4 minus a strong acid or weak acid? Well, HSO4 minus is a weak acid. It's one of the stronger weak acids, but it's still a weak acid. And so we're here, HSO4 minus, weak acid. What do weak acids do? Do they completely, partially, or Not at all. They partially hydrolyze. And so weak acid partially hydrolyzes means that this second step does not go to completion. And so what we do is we draw a small arrow forward and a big arrow backwards. This is one way, completion. Oh, the arrow got screwed up here. I would have drawn it like this. Let me just edit this slide. There. Oops. I guess I can't flip it. So this second one, I draw a big arrow backwards and a small arrow forwards, and then get rid of this arrow here. So it looks something like this. You know, to kind of indicate that, you know. Sometimes you don't have to draw a big arrow. Instead, well, you just draw same size arrows like this. That's okay too. That shows more of a, you know, not complete one way. This is one way. And so this is one way of drawing it, you know, to show that this is a weak acid. So water is going to have a lot harder time plugging the proton off. Water has an easy time plugging the proton off with strong acid. Water has a tough time here. But this is one of the stronger weak acids. This is a much weaker acid here. Acetic acid is way weaker than HSO4 minus. And so acetic acid, water is going to have an even rougher time. And so this should have an even bigger arrow back. But rather than drawing unequal sized arrows, we just draw the same size, and then you're supposed to know. You're supposed to know. But if you don't know, this just registers that something's different here. And so acetic acid is quite a bit weaker than bisulfate. So that's why. And so this is the general reaction here, hydrolysis. But you know, this hydrolysis, like I said, is a hassle. This is not. This is kind of ridiculous here. All right. Because people don't visualize it like that. You can't tell the difference between the hydrogens. When three hydrogens attach to water, you can't tell the difference. And so I like this. You know, this is kind of a hassle to write, right? It takes up too much space, so this is easier. But we know something about H+. This is why I put it in quotation marks. H+ is too unstable to exist below water. And so whenever we see this, you should know it means this. Okay, well, we already talked about that. And so we already talked about this. You know, I have it organized a little differently. You know, strong acid. Strong acid ionize almost completely or completely. I just said completely. The degree of, you know, so I don't take it too literally. It loses its proton readily. Excellent conductor of electricity. Major species are ions. Major species are the ions. Minor species are zero, because minor species would be the molecules, unionized molecules. There are no unionized molecules for strong acids. So there are no minor species here, unless, you know, it depends on how strong. You know, there are stronger strong acids and weaker strong acids. So it might be a weaker strong acid. Weak acids partially ionize or partially hydrolyze. So the major species are different. The major species for weak acids are the unionized molecules, and the minor species are the ionized molecules. So what are we looking at here? Comparison of strong versus weak acid at the. Here, this is strong acid in the beaker. You can see the light bulb's pretty bright. Here's a weak acid with the same concentration. So weak acid only partially ionizes. Strong acid completely ionizes. So it's going to form a lot more ions here. See, here, rather than showing the H+, what are these? You see 3 whites and 1 red? Hydronium. So here they're showing the hydronium and the chloride. So this is HCl, hydronium and chloride. Over here we have acetic acid. Over here we have an acetate and the hydronium. Most of the acetic acid molecules are unionized. They're intact. Just one of them here is ionized. Acetic acid. So since we don't have that many ions, it's not going to conduct electricity as well. Since it doesn't conduct electricity as well, it doesn't light up coal brightly. Here's some numbers if you want to make a comparison. You know, hydrochloric acid is a strong acid. Hydrochloric is a weak acid. Here's the formula. Here's the percent ionization. The percent ionization, these are called concentration units. This capital M stands for molarity. But you know, it's it's 99+% ionized at this. At a little higher concentration, 10 times higher concentration, it's around 80% ionized. Versus hydrofluoric acid, look at the percent ionizations are way smaller. So we represent this in different ways. HCl, we don't, we're just going to assume it's complete or near complete. And then you just draw one arrow here. It goes to hydronium chloride. Over here, HF only partially ionizes, very little, and so big arrow backwards. That's not ionization, that's what we call hydrolysis. The major species in an HCl solution, the major species are the ions. In HF, the major species are the unionized molecules. The minor species are the unionized molecules. In HCl, you aren't going to find very many. In HF, the minor species would be the ions, hydronium and fluoride, or hydrogen ions and fluoride ions. That's all the other stuff we don't. The 7 common strong acids, we already did that. Identifying major and minor species in solution. Let's try that. Nitrous acid and chloric acid. All right. Write the formulas of the major species in solution of nitrous acid and chloric acid. So let's start off with nitrous acid. Nitrous acid is HNO3. HNO3 is called nitric acid. Nitrous acid is HNO2. And so we ask ourselves this: strong, weak? Is nitrous acid a strong acid or weak acid? It's a weak acid. Weak acids, partially hydrolyzed. Partially means the major species will be the unhydrolyzed or unionized molecule. And so the major species for nitrous acid will be HNO2 molecules. And a small fraction of those will actually dissociate in water. Chloric acid is a strong acid or weak acid? It's a strong acid. Strong acids completely dissociate. And so you have 2 choices, H+ and chlorate, or hydronium and chlorate. Chlorate being ClO3. Chloric acid. So which ones can conduct electricity better? Chloric acid. All right, now we're going to talk about reactions. Now, the way I'm approaching reactions is a little differently. Let me show you something. Go. the way I approach solubility rules is a bit differently too. This is a more comprehensive list of solubilities, but you know, do you want to memorize this chart of solubility? The solubility rules, 2 pages. Maybe it's not that long, but do you want to memorize that? No. Let's see how they organize chemical reactions here. Let me just fast forward here. Do you want to memorize chemical reactions like this? Element plus salt, or element plus strong acid. Oxidation reduction type, single replacement, element plus salt, element plus ion, element plus ion. 2 salts or salt, strong acid, or salt hydroxide base, precipitation, double replacement, 2 salts, 2 ions, precipitate. Strong acid plus hydroxide base, molecule formation, H2O, neutralization, double replacement, salt plus water, H plus plus OH minus, H2O. Weak acid plus hydroxide base, molecule formation, H2O, neutralization, double replacement, salt plus water. Strong acid plus salt of weak acid, molecule formation, double replacement. Strong acid plus carbonate or hydrogen carbonate, strong acid plus sulfite or hydrogen sulfite. Ammonium salt plus hydroxide base, on and on and on. Do you want to memorize reactions like that? No, I think to me this is just too much. Too much. And you know what? This isn't even comprehensive. This is missing so many reactions. And so this is like a snapshot. This is like the Wikipedia. You know, let's pick some reactions that seem pretty interesting or common. And so this is why I want to totally reorganize the chemical reactions, because I think this is, you know what this is called? This is called thinking inside the box. If you think inside the box, this is all you can do is what's inside the box, right? If anything lies outside this box, then forget it. You know, you'll have to think outside the box, but how do you think outside the box when all you're accustomed to is thinking inside the box? And so this is why, you know, it's a pain. It might seem like a pain because the book is not aligned with what I'm talking about, but it's way easier than this, you know, I think. And so anyway, we'll I think, what time do we go till today? 25? Okay. Tuesdays are 20, I think. That's all screwed up. You know, Mondays are 35. Is it 20? Yeah. All right, so what we're going to do is we're going to just bear with me, and we're going to try to think outside the box and organize this a little differently, okay? And then hopefully it works out.